Hello everyone, welcome to the first session on the last day of ICCP. We have 4 interesting physics optics abstract talks lined up for today. The first talk is Non-invasive focusing and imaging in scattering media with a fluorescence-based transmission matrix. The authors are Jonathan Dong, Antoine Banfas, Silva Geigen. The video is narrated by Antoine Banfas and Jonathan Dong. Let's watch a pre-recorded talk now.
Hello everyone, my name is Antoine Boniface, and today with Jonathan Dong we are going to talk about non-invasive fluorescence imaging through a scattering medium using a transmission matrix approach. And this work has been done in Paris at Laboratoire Castres under the supervision of Professor Sylvain Gicon. So fluorescence imaging is a wonderful tool and it's widely used in biology. First, it's relatively easy to use, and also it provides nice features in terms of imaging. You have quite good contrasts, like fluorescence is a good contrast. It's also very specific because you only take the light that is emitted by the object of interest, and it's also high resolution, which is around 1 micron. That's very good if you want to image cells or neurons, as you can see here on the right. The problem is that if you want to apply the same thing in depth, so after a few millimeters of tissues, basically it doesn't work. So here on the left, what you can see is the propagation of a laser beam through biological tissues. And what you can see is that after 1 millimeter, so beyond 1 millimeter, you reach the diffusive regime. So in this regime, light is completely scattered. You don't have any ballistic light, the light that is normally used in conventional microscopic techniques. So in that regime, so if you shine some light through 1 millimeter of biological tissues, basically what you get is a speckle pattern because you shine some brilliant light like a laser source. And this figure of interference, of course, so you have some light, you have some scattered photons, and this will excite, for instance, the fluorescent structures that you might have here inside tissues. And all this fluorescence can be backscattered by the medium, for instance, and you can detect it on the camera. But as you can see here, so you still have some fluorescence on the camera, but you completely lose the information about the sample. So you cannot do anything here using scattered light, using conventional techniques. So you need to do something. And the idea was to develop wavefront shaping techniques. So the idea in wavefront shaping is to characterize how light propagates through the medium, and then use this characterization to either control or retrieve information at depth. And the tool of interest, the device you use here is a spatial light modulator. That is a matrix of pixels that can be used to optically, locally change the field. And here I just want to present to you a simple approach, which is the transmission matrix technique, where you somehow measure the transmission matrix, which is the signature of the medium. So basically you display a basis of modes here on the spatial light modulator, and you try to retrieve from the camera sensor the output field. And then you have this linear relationship between the input field and the output field that is here the transmission matrix. And you can use this operator to control light, so you can focus light in transmission, and you can also use it to do some imaging. And the point here I want to stress on this slide is that if you want to apply a measurement of transmission matrix inside biological tissues, you need to place the camera or the sensor inside the body, which is of course highly invasive, and you cannot do that for biological applications. So you need to think of something like this, where you can put the camera or the sensor outside the body, because you need this feedback to do the characterization, and then you use some reporter from the plane or the position where you want to control or measure some information about the object, or control the light you want to send inside the body. So you might want to use acoustics, fluorescence, optics, any type of things. And here we want to use fluorescence. So we want to see if we can combine linear fluorescence from fluorescence microscopy and wavefront shaping. So the thing we have is that we use these spatial light modulators from the wavefront shaping community, where we can somehow change the wavefront of our light, so the way we excite the sample, the fluorescent sample. And the thing we can measure non-invasively is this fluorescent speckle. So this is basically the fluorescence that is emitted by the sample and backscattered by the medium, and you can detect here on the camera, which is placed on the same side as the illumination. And before going into the details, I want just to go back to something very basic, where you can think of the most simple fluorescence object we can have is just fluorescent beads with diffraction limited. So you place this bit behind the scattering medium and you shine some light on it. So here you shine some laser through the medium, it will excite the bit, and you can detect on the other side, so on the same side as the illumination, this fluorescent speckle here, which is a signature of the bit. So of course, then if you change the position of the bit, you will get a different speckle pattern, and so on and so forth. And now you can place 3 bits behind the scattering medium, excite them uniformly with the same weight, the same intensity. And what we get here on the camera is the fluorescent speckle, which is the sum, the Hickorean sum of all the bits, okay, of all the fluorescent speckles emitted by the different bits. And now we use here current light, okay, so what we get actually in the plane of the bits is not a uniform, it's not a plane wave. We don't have a uniform excitation for all 3 bits. We have something which looks like a speckle pattern, so you might end up with something like this, where one bit is more excited than the other ones. So in that case, for instance, the bit number 3 is more excited than 1 and 2, and then it will contribute more to the overall speckle you can detect on the camera. So we can somehow renormalize, if you want, this spatial information, so all the signature by the different bits, and we can put some weights here that translate the way we excite the bits, so H1, H2, and H3. Because of course the contribution of each bit is different, and this depends on the excitation. So we have 2 things, the excitations and the fluorescence emission. The nice thing is that if we are able to shape the light, the incident light, so for instance using a spatial light modulator, so we change the wavefront of our light and then we change again the speckle pattern we have in the plane of the bit, we are able to change H1, H2, and H3, which are the weights, the way we excite the bits. But the nice thing is that all the speckle patterns here, all the signature from all the bits, they remain the same if the bits are at the same position and if the scattering medium is static. And now if we try to translate it with the matrix formalism, what we can say is that we have 2 independent things. We have the excitation again and the emission. And we can say that it's a matrix multiplication between W and H. And W is the way light is backscattered by the medium, so from the bits to the camera, and H is the intensity matrix again from the spatial light modulator to the plane of the bit. And what's interesting is that H, this matrix here in intensity, is connected to the field matrix that connects the input field to the output field, the one I described at the introduction. And now all the question is, so from this measurement, so we know the input field will display on the spatial light modulator, and we can measure easily with the camera the speckle pattern, the fluorescent speckle pattern. Can we use these 2 information to retrieve W and T?
Let's describe how this double transmission matrix reconstruction is performed. First, we need to collect experimental data. To do so, we send random SLM patterns as inputs and collect fluorescent images at the output. We thus want to solve an inverse problem given these pairs of input-output data. Here, an important assumption comes into play. We assume that the number of fluorescent targets inside the medium is small compared to the number of patterns we send. We can thus represent our setting as described previously, with a set of eigenpatterns and weights describing the excitation for each SLM pattern. Hence, if all the collected intensities are put in a large matrix, this matrix is low rank, with its rank corresponding to the number of targets. We write it as W times H, and moreover, both W and H are positive valued matrices, as they correspond to intensities. For this reason, we start our reconstruction pipeline with a non-negative matrix factorization algorithm to recover W and H from the knowledge of I. This outputs the second Tn W, and we still need to obtain the first one. For this one, it corresponds to the classical single transmission matrix case, thanks to the relation H equals modulus square of T times E in, where we know both H and E in. We use a phase retrieval algorithm to find T. At the end of this pipeline, we have reconstructed both T and W and characterized the in and out scattering process. We demonstrate this approach experimentally. A good way to check the quality of the reconstruction is to use these transmission matrices to focus light back on the targets, a technique called phase conjugation. These are, for example, the results on our experiment, where in the first line we have the fluorescent images, and in the second, the excitation at the plane of the beads for control. We see that sometimes a few rows of the TM are not valid, for example the second one here, but we can clean the matrix to keep only the rows where focusing is successful. Furthermore, we see in control that we can use objects with a relatively high number of bits, and that we are able to identify most points in this object. This proves that the reconstruction has been successful, and that the pipeline is robust enough to be applied in real-life conditions. We then want to leverage this information about the scattering process for imaging the occluded object. This is possible thanks to some special correlations called memory effects. The principle is quite simple. If a point source is moved a little amount, the output speckle is also translated. This is only valid in a small range, defining a memory effect range. One can, for example, obtain 2-photon fluorescence images by scanning a focus in a small field of view. Thanks to our previous focusing experiment, we have the information to exploit these memory effects. For example, if two beads are close, as depicted in these control images, then the two corresponding fluorescent images are shifted versions of each other. We can see that by computing the cross-correlation between them, as it presents a bright peak. If we fix the first target and compute the cross-correlation with all the other focus positions, we obtain such an image, where we can clearly see the memory effect range, after which the technique does not work anymore. Then, it is possible to continue with another focus position as the origin, and we can reconstruct an extended object, neighbor by neighbor. In this case, we have successfully imaged an object a few times larger than the memory effects. Finally, our formalism based on low-rank approximation and focusing on targets can still be applied to continuous biological samples. For example, here are some images of pollen seeds hidden behind a scattering medium. We see that the pipeline is robust enough to account for these more complex objects. In conclusion, we have developed a technique for non-invasive linear fluorescence imaging. A double transmission matrix model had been introduced, and reconstruction was performed thanks to a two-step reconstruction with NMF and phase retrieval. This allowed us to focus excitation on the target and image beyond the memory effect, even complex biological objects. With that, we would like to thank you for your attention, and feel free to write us your questions to continue the discussion.
Thank you, Jonathan and Antoine, for such an exciting talk. I believe the audience are posting questions in the live chat. Before that, I have a couple of questions of mine. The first question, your technique recovers fluorescence transmission matrix, right? Why do we still need memory effect? Can we not use fluorescence transmission matrix to recover the bead positions?
So we need the memory effect to do the imaging part. So to measure the matrix, you don't need the memory effect. The memory effect is just for imaging. You need for some information between the bits if you want. So that's the information you can only get with the memory effect. So you need the correlations here.
Yeah, I want to follow up on that. Why not take the measured image and then do something like fluorescence transmission matrix inverse times the image, and won't that be the image of the beads?
Basically, here we are based on a low-rank approximation. So if we do that, we get some results, but we can't localize the particles. We don't know where they are. We can just say how much each target has been excited in time, but then we can't localize them. So that's why we need the memory effect.
Okay.
But it's an interesting thing.
Thank you. I'll ask one more question, the last one. I feel there are two potential limitations in this really cool technique of yours. One, we need the prior knowledge of n, the number of fluorophore beads, and also two, the fact that there is n, which means like you're assuming that the scene is sparse. So are these like really the limitations of your technique, and is there a way to potentially overcome these limitations in the future?
So yeah, that's true. It's a good point. So about the rank of the matrix, it's true that this is input parameter you need to somehow compute and like retrieve the matrix. And we showed here that it's not very important. You can overestimate the rank and somehow remove afterwards the values that are either noise or double. If you double, for example, you have the same line, so you focus twice on the same bits. You can see it with the speckle information. So it's possible, and the what we say here is that we can overestimate the rank. And then I think the second question was about the I missed, what was the second part?
Sparsity. I mean, are you limited to sparsity?
That's a good point. Of course, it's like if the object is you have like a lot of diffraction limited source,
it means that the speckle at some point is very low contrast, so you cannot do anything. So we need some contrast here to retrieve information. So here it comes from the sparsity. If you have an object which is more complex, then you need to increase the contrast, so you can use some filters to make sure that you have only few spectral components of the fluorescence that are retrieved on the camera. So there are some tricks, of course. If you have like something quite homogeneous and very broad, it's impossible to get any information from there.
Okay, makes sense. Thank you so much, Jonathan and Antoine, for your time. Due to time crunch, we have to move to the next talk. Please monitor the YouTube live chat and answer the questions posted by the audience. And audience, please post all your questions in the YouTube live chat even after the session, so that the session, the paper presenters can answer your questions. The next talk in this session is Multipath Echo 3D Image Reconstruction. This is also a physics optics abstract talk. The authors of the paper are Valentin Capitani, Alex Turpin, Jack Radford, Davide Rovelli, Kevin Mitchell, Ashley Liu, Ilya Stashinov, Daniele Faccio. Let's watch a pre-recorded talk now.
Good afternoon. Today I'll be giving you an introduction into using multipath echoes for 3D image reconstruction. This is work carried out at the Extreme Light Group of the University of Glasgow. This work relates to a third imaging paradigm that we are actively researching. So normally when one thinks of imaging, one thinks of flood illuminating a scene and then redirecting the reflected light using the lens onto a pixel array. So this is what cameras do. Another method is to use structured illumination. So we illuminate a scene with structured light, sample it onto a single pixel, and then we build up our image of our scene using several different patterns. For instance, this is how point scanners work. They would scan through the scene, or how single pixel cameras also work. Our third imaging paradigm is to use pulsed flood illumination and a time-resolved single pixel. So what this does is illuminates a scene with no spatial structure and detects the scene with no spatial structure. All we have is the temporal trace of that scene. And this brings us to why we want to use multipath. So for a single scattering event, our imaging paradigm fails in the lack of a background anyway. And you can imagine this here in this image. If I have a transceiver here, emitting and receiving a signal, and then I have a point scatter here, the transceiver will emit a signal, it will reflect off of the point scatter, and it will arrive back at my transceiver. And I will get a spike corresponding to the time of flight of that signal. From this time of flight, I cannot deduce where exactly the object is. All I know is that it's somewhere on the radius determined by the distance corresponding to this time of flight, somewhere on the dome with a given radius. It could be anywhere though. However, if I also incorporate the second and in particularly the third order reflection, so it's a 3-path event, meaning we have 3 scattering events before arriving back to the camera. If I include these higher order scattering events, for instance, the 3rd path event is I have light hitting the object, reflecting off of the wall, reflecting back off the object, and then arriving at the detector. Then I can exactly tell where my object was if I know my position next to a fixed wall, because the difference between the 1st and the 3rd path event is the distance between the wall and the object. That will allow me to unambiguously deduce the 2D position of this object. And this can be extended to more complex environments and 3D using machine learning. Now, previous approaches have relied on blocking out a portion of a fixed background. So if I have a fixed background behind a scatter, then light cannot reach that background portion, which is exactly behind the scatter. So a machine learning algorithm can associate the corresponding dip in the background signal with the object position. The second option is to limit yourselves to calculating the relative positions of a few sparse point scatterers in a narrow field of view, illumination field of view. However, we are looking at to image more complex scenes where the second approach would fail. that brings us to our question, which we have confirmed, is whether multipath data allows for better 3D image reconstruction than single path data in this given imaging paradigm. So for this, we've built a simulation which allows us to control the number of scattering events in our temporal histograms with perfect precision. So our scatterer is a block, cuboid, moving around in a room. And we use a Monte Carlo ray tracing algorithm to sample our scene. We emit 10,000 photons and observe how they reflect. And basically, we are just firing a photon. This photon bounces around in the scene. If it happens to arrive back at a surface, which we denote as the temporal detector, then we get a spike and we detect it. Sometimes, of course, it will not arrive back at the detector. Sometimes it will just bounce around the scene. And sometimes we have a trivial solution where it just reflects directly back to the detector from the opposite wall. Using this simulation, we build up 10 data sets. Each data set is characterized by a specific maximum number of scattering events. For instance, a maximum number of 5 scattering events would mean that each of the temporal histograms has up to 5 scattering events. It can have 1, 2, and 3, and 4 as well, but it can also have 5 and no more scattering events. And for maximum scattering event numbers from 1 to 10, we build up these 10 data sets. Each of them consists of 2,000 object positions for training, 100 for testing. And with these 10 data sets, we train 10 neural networks, CNNs, to take the temporal histogram and output the 3D image. The architecture is a very straightforward CNN that's going through a bottleneck shape, which is meant to promote the information compression system that would remove some noise and hopefully pass on only the signal that we're actually interested in. And with our 10 neural networks trained, we can then predict the 10 datasets, the 10 test datasets. We found that the mean squared error of prediction, where when we fit only one scattering event, is a lot higher than when we fit multiple scattering events. So this tells us that as we increase the number of scattering events in our dataset, the neural network gives better predictions. You can visually see that here. So this is the reconstruction compared to this ground truth with only one scattering event, with 4 and with 10. And we also observe that this improvement in reconstruction doesn't go up ad infinitum. It experiences a plateau after around 6 scattering events. And this led us on to examine our data in more detail. So we undertook an information theory study, which demonstrated that consecutive scattering events contain uncorrelated information. So what we did is we took our data sets with X and X minus 1 scattering event. And for these two data sets, we calculated the number of bits of uncorrelated information that we're getting. I've included the formulas for that here. And what we found is that as we're increasing the number of reflections in our data set, we get first a large increase in uncorrelated information, followed by an eventual rapid decrease towards 0. So when we have 6 scattering events versus only 5, we're not getting any new uncorrelated information. And this was pretty interesting. And it also follows the pattern of this plateau, that eventually we're not getting any new information that gives us a hint as to why we're not getting any improvement in our reconstructions. But a more conservative way of looking at this, or a more intuitive way of looking at this, is to consider what happens when we project light onto a scene. This scene contains this one figure shown in black, and the direct reflection will just be this black silhouette. If we then look at the reflections, so multipath reflections in the scene, we can see the red silhouettes with four path events, and we can see that we observe multiple perspectives of the object. We can see the back perspective, the side perspective of the object as well. So we really have a lot more information about the exact object and the exact position of that object. As we increase this further, up to 10, we get the teal full-on Hall of Mirrors effect. And these teal reflections are actually degenerate replicas of the same perspectives that we've already seen in our four-path scattering event. And this gives us another intuition as to why we don't get any further improvement beyond a certain point. We're just seeing degenerate replicas of perspectives that we've already seen. However, all of this was done in simulation, so we confirmed the advantage of multipath data experimentally as well. For this, we used small and robust radar, as well as some off-the-shelf acoustics, in particular because such transceivers use wavelengths to which everyday scenes appear reflective. Hence, they would observe a truly multipath signal, unlike, for instance, many laser-based LiDAR systems. We can simulate various scattering event counts by cropping portions of our temporal signal. So we have our, for instance, for acoustics, we have our loudspeaker emitting sound waves. We measure the returning waves on a microphone, and that gives us a temporal signal as shown below. And if we want to simulate a one-path scattering event time signal, we would crop out the parts of the signal that correspond to a time of flight that's larger than the first reflection from the far wall and back. And then we can do similar things with our radar signals, and we can build up data sets corresponding to approximately various scattering event numbers. And what we do, what we see when we do this, and we train neural networks for each of these cropped data sets, is we see monotonic improvement with the increased time duration of the larger scattering event data sets. So as the amount of time that we are measuring for in the data set is increasing, we get a nice decrease in mean squared error, corresponding to an increase in the reconstruction quality, which you can also see visually, the reconstruction quality getting better, closer to the ground truth. And this gives us a nice side advantage to this project, is we've been able to convert radar devices, which are small, transportable, highly accurate within a few meters, and which is more convenient than a laser system in many ways, as well as acoustic systems, which are readily available for most people on your smartphone or on your laptop. We've been able to convert these convenient systems into 3D imaging devices using or exploiting machine learning and multipath scattering events. That concludes my presentation. For our full research, I've included the link to our publication. And if you have any questions, please feel free to write me an email. Thank you for your attention.
Thank you, Valentin, for your insightful presentation. I'll kick off the Q&A session with a couple of questions of mine. It seems that your technique can image occluded scenes. Did you try to image something like non-line of sight scene geometry with your technique, or is it lined up for future work, something like that?
In this work, we were focusing on line of sight. It's lined up for the future, and we're currently working on non-line of sight implementations. So, yeah.
Okay. It seems to me that the scene has to be extremely specular, almost mirror-like, for what you referred as third imaging paradigm to work. For visible wavelengths, especially, the world is very diffuse. Does your imaging technique still work in that case?
Yeah, so our imaging technique, our imaging paradigm rather, does work in that case as well, if we can assume that we have a fixed background and we're blocking out some portions of that background. And based on how much we block out, or which part of the signal we block out, we can locate ourselves with respect to that fixed background. However, yes, you're completely right. And this is why in this work, where we're focusing on multipath, we used acoustics and gigahertz wavelength radar, because these appear, to these wavelengths, the world appears a lot more reflective than to visible wavelengths, but absolutely correct.
Okay. We have a question from the YouTube live chat. Vishwanath Sargadam is saying, very insightful talk, especially the Hall of Mirrors effect. He's asking, would the multipath effect also allow for increase in resolution beyond the wavelengths? I think he's referring to the diffraction limit. Can you image beyond diffraction limit is his question?
Yeah, so maybe you don't see this, but our host, Yannis, they have actually done some work before on overcoming the diffraction limit, the spatial diffraction limit, by abusing the fact or exploiting the fact that two spots which are at a fixed distance, if they move further from you, the solid angle will become smaller, but their absolute distance does not, so their temporal distance also does not shrink. So this does let you break the diffraction limit, but this is not really what we are focusing on. But very good question, thank you.
Okay, that's all the time we have for the Q&A session. Please look into the YouTube live chat for more questions that will be posted there. We'll move on to the next talk. The next talk is distortion matrix imaging for aberration correction over multiple isoplanatic patches. The authors are Paul Bolandrade, Amaury Baden, Victor Barolle, Ulysses Najar, Christina Irsch, Claude Bocara, Matthias Fink, Alexander Aubrey. Let's watch a pre-recorded talk now.
Hi everyone, I'm Paul Malandrade from Institut Langevin in Paris in France, and I will present you the work I've been doing with Alexandre Aubry on a matrix approach for correcting aberration and multiple scattering inside biological tissues. So aberration and multiple scattering are the major limitation to microscopy for imaging tissues in 3 dimensions. So here we would like to focus light on the focal plane of a microscope objective through an aberrating layer. So due to the aberration, the light is spread out and the resulting PSF, or the resulting focal spot, is larger than the diffraction limit. So this drastically affects contrast and resolution of the image, as you can see here on the right part of the slide. And so to overcome this issue, some techniques exist, and these methods are usually called adaptive optics. So the basic idea is to find the right phase distortion that light has encountered during the propagation in the media, or equivalently here through this aberrating layer. And then, by using a SLM, a spatial light modulator, the idea is to pre-compensate the wavefronts in order to recover, at the end, a diffraction limited spot in the focal plane. So this correction is valid for a limited area on the focal plane of the microscope objective. This area is called an isoplanatic area or an isoplanatic patch. So this is exactly the part of the field of view that have seen the same aberration. So here on the figure it's circled in green. So now if you want to focus on another part of the field of view, the correction will not work anymore. This is one of the main limitations of adaptive optics. So to go beyond these standard adaptive optics techniques, we developed here at the Langevin Institute a new approach based on the linearity of the scattering process. So this approach is called a matrix approach of microscopy. And so here we consider first two plane and the sample. So an input plane or an emission plane, which can be a galvanometer or a SLM, and also an output plane or reception plane, which can be a camera. So the idea is to measure the reflection matrix that contains all the impulse responses between all the pixels of these two planes. So this matrix, this reflection matrix contains all the information available on the media, and we only acquire one matrix and then do the aberration correction process on the computer. So the ultimate goal for us is to retrieve in a non-invasive way a transmission matrix between one of the two planes explained before and a fictive plane inside the medium. So we can say that we would like to retrieve an adapted focusing phase law for each pixel in the image. So here is the setup to measure a time-gated reflection matrix. A femtolaser illuminates the sample, and two galvanometers here scans the focal spot. And for each focusing point, we record the output backscattered wavefront on the camera. The camera plane is conjugated to the microscope objective pupil plane. And so by scanning the focal plane located by the coordinate r in, all the backscattered wavefronts are stored in the reflection matrix in the dual basis, so focused at the input and pupil plane at the output. Then, by performing a 2D Fourier transform on the output coordinate, we have access to the matrix in the focus basis. So, if you look at the diagonal elements of this reflection matrix in the focus basis, it's the element for which R in equal R out. So you try to focus at one point inside the medium and you look at the energy coming only from this point. This is the confocal image. But with this focus matrix, we also have access to the strength of the aberration. So we can quantify how the energy is spread out the focusing point due to aberration and multiple scattering, and this corresponds to the off-diagonal elements of the matrix. So here you can see a point spread function in reflection deduced from this focused reflection matrix. So we applied this matrix characterization of aberration to an ex vivo mouse brain tissue with high numerical aperture microscope objective. So here are plotted the reflected point spread function for different depths inside the brain. So you can see that for the first layer, all the energy is located at the center of the point spread function. But when you go deeper inside the brain tissue, due to aberration and multiple scattering, the PSF is really spread out. So you can quantify this with the Strahl ratio, which is exactly the ratio between the single and the multiple scattering, and this ratio drops regarding the depth inside the tissue. So how can we compensate for this, for aberration that really prevents us from imaging deep inside the tissues, such as the brain tissue? So to do so, we implemented a new operator called the distortion matrix, the distortion operator. So this new operator will contain only the distorted part of the backscattered wavefront by the sample. So let's look back at the setup I showed you just before, and to summarize, there is first the reflected part from the sample that contains two contributions. The first one is the geometrical part corresponding to the area on the focal plane where the focus is done, and also the distorted part, which correspond to the aberration. So here we add a reference arm that mimic exactly the propagation of the sample arm, but without any aberration. So now, so what we measure is by interference exactly the phase difference between these two arms. So by interference, we measure only the distortion of the backscattered wavefront from the sample. So now, two focusing points close to each other in the media will have seen almost the same distortion. So this matrix has now a lot of correlations between the different backscattered wavefronts, and the idea is to extract this correlation now. So to do so, we can perform a singular value decomposition of this distortion matrix in this dual basis, and under an isoplanatic area, the rank of this matrix is equal to 1. So we can monitor this hypothesis with the weight of the first singular value over the other ones. And we can take advantage of the aberration invariance to extract an adapted focusing law on each isoplanatic patch. So the first singular vector of the SVD corresponds exactly to this aberration focusing law. And with the SVD, it's as if we have created a virtual reflector inside the media that have seen the aberration. But in reality, the brain is not isoplanatic. So the idea is to subdivide the field of view into a set of isoplanatic patches based on the optimization of the first singular value of the decomposition. So here I plot the first singular vector from the decomposition and in the pupil plane, and that's this aberration corresponds to an area on the field of view which is isoplanatic. I can do this on another part of the field of view, and then I can recover the transmission matrix between the pupil plane and all the image pixels on the focal plane. So here I will present you the results I had on a brain slice. So what is important with the matrix approach is that it's possible to recover both the output and input aberration by numerically propagating the matrix to the different bases. So here I first show the input local correction. This phase map corresponds to the aberration phase law in each isoplanatic area. So it's we can see both some defocus and high order aberration, and the typical size of the isoplanatic area on the focal plane is 5 microns. Now at the output we can see this different aberration phase law which corresponds to different isoplanatic area on the field of view. And we can see that there are some differences between the input and the output, and this is due partly because the sampling at the output is larger than at the input, and because the different position of the input and output plane is quite different, and it's hard to make these two planes match together experimentally. So finally, I plot here two images. First, the confocal original without correction and after correction. And also, I plot the point spread function before and after correction. So what you can see is that some new structures appears and the contrast is largely increased on the confocal image, and we can see some new fibers that appears, which is typical for this kind of tissues. And what is really important is that we are able to refocus the energy at the center of the PSF after correction by a factor of 10 in intensity. So I presented you a new way to numerically quantify and correct for aberration in a non-invasive way. And what is important is that we can correct both at the input and the output over a multiple isoplanatic area. So thank you very much for your attention, and if you have any question, it will be a pleasure for me to answer.
Thank you, Paul, for such a cool presentation. I have a couple of questions for you. First one is a technical clarification question. For the time-gated reflection matrix, you will need a transient camera, right? Which transient detector did you use? And maybe you can comment on how the temporal resolution of this camera affects your approach.
Okay, so for the time gating matrix acquisition, I use a classic CCD camera, and then it's a femto laser that illuminates the interferometer that makes the time gating. So the axial resolution is almost 10 microns.
Okay, that would be like in some couple of picoseconds, I believe, or less than that. But
sorry?
Okay, 10 microns is the axial resolution that you get. That makes sense. I have a question from the YouTube live chat. Ankit is saying, a very cool talk. And he's asking, do you have plans to extend this to in vivo imaging? If so, will movements in the scattering media due to breathing blood flow impact the measurement of the distortion matrix?
Yes, exactly. So the movement makes some distortion on the measurement of the distortion matrix, but maybe we can use this movement to get disorder and make the singular value decomposition converge towards the good singular vector faster. So maybe it can be a good point to use these movements. And the idea is now to implement this setup and this approach to a physical aberration correction with a spatial light modulator.
Okay, makes sense. Thank you, Paul. We have one more question from Orikats. Orikats is saying, thank you for this great talk. And he's asking, What are the requirements from the target for the SVD approach to work? Would it work on an extended object with no sharp features?
For the SVD, we need to have in speckle. It's okay. It can work in speckle, but we need the SVD to converge. The first singular vector need to converge towards the aberration phase law, and for that we will need to have enough independent scan inside the sample in only one isoplanatic area. So maybe it's the main limitation, I think, of the singular value decomposition.
Okay, makes sense actually. So thank you, Paul, for your time. We will move on to the next talk. Please monitor the YouTube live chat and answer the questions posted by the audience there. Okay.
All right.
Thank you. Let's move on to the next talk. The next talk is designing a simple pre-filter that makes cameras more colorimetric. The authors of the paper are Yutang Ju, Graham Finlayson. Let's watch a pre-recorded talk now.
Hello everyone, it's a great pleasure to give my presentation in this year's ICCP conference. My name is Zhu Yuteng. Currently, I'm a postdoc in the Color and Imaging Laboratory, University of East Anglia, United Kingdom. I'm co-author with my supervisor, Professor Graham Finlayson. Our specialty is to use physical and mathematical modeling to solve color problems in color imaging. We'll be working on how to tackle the colorimetric problem of digital cameras, and we propose to design a specially selected color filter that when this filter is placed in front of the camera, this filter plus camera settings can see the colors more accurately. So in the sense that it becomes more like that perception by human observers. Our research question arises from the fact of the disparity of systems between a digital camera and our human visual system. We propose to tackle the problem by designing a transmissive color filter to be placed in the optical pathway between the inside light and the camera sensors. So we have designed such a filter through mathematical optimizations to best satisfy certain criteria. Firstly, we propose that the camera after filtering best satisfy the so-called Luther conditions. The Luther condition requires the camera sensitivities to be a linear transform from the color matching functions of the human visual system. This method mainly focuses on the sensitivity response of the camera, but it takes no consideration of the real-world object that the camera are capturing. So we later proposed a data-driven method that takes the real-world illuminance and the surface spectral data into a design. Lastly, we also consider the feasibility of a filter solution for manufacture in the future by adding some necessary constraints into the design. A brief conclusion ends the talk. So let's walk through a bit of the background of the color formation process. The physical process of forming the color information involves three key elements. First, the light source, the object, and the observer. It starts from the light emitted from illuminant and reflected or transmitted by a surface before viewed by an observer. Colorimetrically, we can quantify a physical color by integrating their spectral information, so including the spectral power distribution of the illuminant, the reflectance factors of the surface, and the color matching functions of the human observer. It's all calculated over the visible spectrum, normally from 400 nanometers to 700 nanometers. So as a digital camera, it works the same way, and the digital cameras are designed in an analog way of the human eye for forming a triplet values for color pixels, known as RGB values. So if a camera is to capture colors exactly like a human observer, arguably the camera sensors should equal that of human photoreceptors. In this way, RGB values a camera records match those of the quantity of the human observations. But however, as we know that engineering cameras have quite different spectral sensitivity functions from the human eye, so as the curves shown here. For most practical applications like photography and video, it's more useful to transform the recorded RGB values to drive a display so that image captured by camera records triplet values of that can reference to the human visual system. So the common way and most applied way is to use a 3x3 linear correction transform. But as we see here that after this linear correction, the fit of the linear transform is not perfect. And we can see there's still big gaps between the sensitivity curves, so which makes it not sufficient for applications which demand high color accuracy. So our proposal is to design a specially selective pre-filter, so which will change the camera sensitivity functions in such a way that it minimizes the mismatch between human visual system and the digital camera. So with the help of a filter, we hope that the camera can measure colors more accurately and therefore can be used for applications with high demand in color accuracy. So what is the effect by placing a filter in front? Physically, the rule of filter, which absorbs light on a per wavelength basis, can be modeled as multiplication of spectral sensitivity. So specifically, if f lambda is a transmittance filter function and q lambda denotes the camera sensitivity at a given wavelength function, so taking this 555 nanometers as an example, after filtering, so this f lambda q lambda multiplication is a physically accurate model of the effect of placing a filter in front of the camera sensors. Now we can look at how to design such a filter. Firstly, we propose the Luder condition-based optimization method. Given the spectral sensitivity functions of the camera, Q here, and the human visual system sensitivity is X, we're looking for a filter F that when it multiplies with the camera sensitivities, so it's F multiply Q, as because it's per wavelength based, so we use diagonal of F multiply Q. And then after linear transform M, it's a 3x3 matrix. So it best approximates the target colorimetric function X. So the whole formula is the Luder condition. And it gives us this simple formulation for the optimization. The objective functions here that we're minimizing is the square areas of the sensitivities between two sensor sets, the camera after filtering and the human visual system. So this is a very simple but beautiful formula, as you can see, as well as powerful. And we can solve the filter and the correction matrix in an alternative scheme, so that the filter and the correction matrix, each of them can be solved in a closed form of the least square regression. And we can find a filter that is the effective spectral sensitivities are almost a linear combination from the colorimetric functions. So as we see the curves here, you can see that the curve fit very promisingly. We tested across 28 off-the-shelf cameras, and we find that after filtering, they almost meet the Luder condition and become colorimetric. We then extend our filter design method in a data-driven manner. This method builds upon the system outputs by considering the color formation process. We reformulate the optimization formulation using the real-world light and the surface reflectance data, and the new formulation is like this. So we just put this new matrix C here, which represents the color signal of the real-world illuminant and surface reflectance. And also at the same time, we post the positivity constraints of the filter. And in this formulation, the filter and the linear mapping matrix can be solved in an iterative scheme, and also the filter can be solved because of the constraints using the quadratic programming. The optimal filter solved from a data-driven method provides further improvement comparing to the filters by the Luder condition optimization. One problem we meet is that mathematical solutions usually imply very poor physical solutions. At this example here, it is not at all a good filter in terms of the realizability. On the one hand, for much of the visible spectrum, it absorbs most of the incoming light. On the other, it varies sharply over the spectrum, so these spiky changes can among great challenges to manufacture. We tackle this physical feasibility problem by importing plausible constraints into our filter design. So like we use smooth basis functions to generate a filter, and then we also pose the transmittance bounds. So these constraints are incorporated into the filter design optimizations, and hopefully we can solve for a smooth and relatively transmissive filter. The filter now can be solved using a constrained quadratic programming. And we also consider the local minima issue and apply a sampling method that samples the hyperspace of the parameters. So for example, when we use 8 basis function to generate a filter, to compose a filter, we will sample this 8-dimensional hyperspace. We use like 20,000 sample points to generate this initial filter. So we use this filter set then to see the algorithms to find the best filter solutions. We show that the sampling method can improve largely of the filter performance. Under the constraints and using this sampling method, we found that a smooth and a reasonably highly transmissive filter, like overall transmit 50% of the light, can be found, and it satisfactorily ensures us by offering similar performance to the prior art without any constraints in the minimizations. And we also show that our method outperforms the conventional color correction methods, such as like polynomial and root polynomial with their high orders. And our method outperforms by a large margin. To conclude, we show in our work that we can design and find smooth and reasonably highly transmissive filters that can be used to improve the color measuring performance of digital cameras. And as such, the camera can be used for accurate color measurement. That will be all. Here's my email address. Questions and discussions are more than welcomed. Thank you very much, everyone, for your attention. Thank you.
Thank you, Yutanju, for a colorful presentation. I'll kick off the Q&A session with a couple of questions of mine. I'm wondering where and how does demosaicing fit in your framework?
Actually, we kind of want to keep the whole ISP process in the cameras. So we just try to put a pre-filter in front of a camera. So I think all the rest of the ISP will keep the same. Yeah.
Okay, I want to
so
follow.
It won't affect the mosaic process.
Okay, so you put a pre-filter and you still have a color filter array, and then the data is captured, and you do demosaicing on that. Won't the demosaicing algorithm? Shouldn't the demosaicing algorithm be affected by the fact that now the spectral response of the the color filter array has changed? Will that affect it?
I think it got some point like when kind of the entering light has been filtered, so it will have a slight change.
Okay.
Probably the algorithm might have changed, but I think the process or anything should keep the same.
Makes sense. I'm still waiting for questions for the from the YouTube live chat. I'll have one more question for you. I'm wondering, these days there is this end-to-end optimization using deep learning and everything, right? So does it, do you think that the filter design will be better or will get affected if you use these deep learning techniques and learn not just the pre-filter, but based on the pre-filter, also the color filter array design, demosaicing algorithm, display properties, all of them, can they be learned if you use something like a end-to-end optimization of everything, something like that?
I think it's a very interesting point, yes. So I think deep learning could be one of the tools to tackle like color accuracy problems, definitely, yes. I think our problem is more like on the physical modeling point of view because of the fact that spectral sensitivity of the camera is based on material or other considerations. So it's quite different from the human vision systems. So we try to correct or compensate such disparity of the sensations. So we want to like solve this in the physical perspective. It's not like all on the processing afterwards. So we try to keep it simple and using the original whatever process applied in the camera, but just try to use the physical correction for the camera. It's simpler and powerful. But I think deep learning, I agree with you. Like, yeah, I think because deep learning is like from algorithm point of view, and then you have to have feeding a lot of data. So for each camera, we kind of don't have much data. One spectral sensitivity set is one set. So there's not a lot of training for this deep learning. So our is more simpler and powerful, but I think deep learning have its way in this problem as well.
Yeah. Okay, we have one question from the YouTube live chat. Vishnath is asking, could you comment on how this pre-filtering affects downstream tasks such as better displays or higher accuracy for classification?
So we kind of like this come into for the camera to capture colors more accurately before it becomes the image format, for example, JPEG or PNG, whatever. So we try to make the color more accurate as a basis, and how I think it will improve the accuracy for the detection or classification afterwards. So we are pretty like in the front end of this line. Hopefully it will help.
I agree with you. Yeah, maybe you can test in the future whether everything post the pre-filtering will also improve by a very large margin or not. Thank you so much, Yutan. That concludes our session. I want to remind everyone that we have an amazing keynote session lined up by Ala. And I also want to remind everyone that the next session is a poster session. It's in Gatherton. Let us socialize with our avatars there. Also, we have a best poster award thing. You would have gotten an email already. Choose the best poster by voting on the link that was sent to you. The best poster chosen by all of you guys is going to be announced during the concluding remarks at the end of the day today, which is also the end of the ICCP. Thank you all. See you at the Gatherton and also at the keynote session. Thank you.